So, hello everybody. My name is Andrzej. I'm a solution architect at Software Mill, a Polish software house, and you may know us from our technical blog, Scala Times newsletter, Scala conference, and few other open source activities, mostly from Scala world, but not all of them. And if you are thinking Scala, what the heck? Yeah, I'm the JVM guy, but don't worry, this presentation is not about technology. It's about some concepts, some problems, and some solutions. Also, this presentation is constantly evolving. Currently, it's based on 5 different commercial projects, completely different domains, completely different problems. And the idea was that I will distill the most valuable lessons learned. And yeah, let's see how it will go. Since you've joined this session, I suppose that explaining basics of event sourcing is quite pointless. Probably most of you is already pretty familiar with this concept, but there is no presentation about event sourcing without this set slide. So let's get it over with very quickly. In classic systems, we are saving our entities, aggregates to the database as the most current state. And in case of some changes, we will simply override this state. In event sourcing, state in database not exists anymore. Yeah, you can save a snapshot of the state, usually as a performance optimization, but this is totally optional. What you are saving and what is your source of truth are events. And when you reply event by event from your database, you'll get exactly the same state as on the left side of the slide. So it's shopping cart with 2 items, A and B. But with events, you will also get more business information. So item C was added and then removed from the shopping cart. It looks like a pretty interesting business information. Maybe we should send a voucher for this item to the user. Maybe we should figure out some replacement for this item. Maybe this information is completely or not important at this point, but what is crucial here is that you as a developer should not decide what business facts are important, what's not. You should store all of them and provide necessary data when needed. And fun fact about event sourcing from one of Greg Young's presentations. By the way, Greg Young is one of the event sourcing evangelists. If you don't know this gentleman, well, you should definitely Google him. A lot of really cool materials about event sourcing. So the fun fact is that humans have been using event sourcing for thousands of years. That first, let's say, implementation of event sourcing was found on clay tablets in Mesopotamia 9,000 years BC. And it was used for persisting marketplace transactions, so how many ships, bread loaves, grain were bought or sold. And this way, the Mesopotamian trader could very easily calculate the state of possession. Not by doing this manually, like counting ships or something, just by replaying the facts from these clay tablets. And in 2005, another famous gentleman, Martin Fowler, wrote an article about event sourcing where you can read such a sentence. Enterprise applications that use event sourcing are rare, but I have seen a few applications or part of applications that use it. And this is kind of sad. 11,000 years in total seems like enough time to validate some concept on production, don't you think? Fortunately, we have 2022, or unfortunately, it depends. But yeah, 2022. And from my observations, which are obviously biased, but from my observations, this concept is finally getting more and more popular. Why? Because we are building completely different systems than 50, 20 years ago. And at some point, you simply don't have a choice. To scale, to move forward, to expand, you will either end up with something very close to event sourcing or with full event sourcing adaptation in some places. So I'm observing the same patterns in basically any event-driven system. Why event sourcing? As I mentioned, with event sourcing, you will get complete log of all stage changes in the system. This is especially useful for your business. No data is lost, but for you as a developer as well. Why debugging? So many times when I was trying to find a bug in my system, it was necessary to replay event by event. And trust me, debugging this way is a completely different story. It's like time machine, but more real. You can move backward, forward. It's super handy, especially if you have a really, really nasty bug. Yeah, but from perspective of my clients, they invest in event sourcing solution because of these 2 reasons, performance and scalability. And of course, this depends on the actual implementation. But let's say with event sourcing, it's way easier to achieve these goals. And the last point, finally, with event sourcing and asynchronous, decoupled, event-driven communication works like a charm. And thanks to this pattern, you can embrace this kind of integration much easier, and yeah, it just works. Okay, before we jump into more details, let's talk about one more acronym, which is CQRS, so Command Query Responsibility Segregation. In CQRS systems, the responsibility for handling commands and writes is separated from handling queries and reads. And this separation is not only on a software level, so different repositories, but also on a hardware level, different deployments, different hosts, different databases. And you can implement CQRS without event sourcing, but implementing event sourcing without CQRS is quite pointless. I mean, you can, but it will be really, really hard to squeeze maximum potential from event sourcing without CQRS. That's why these two are implemented more or less together. And during my journey with event sourcing systems, I extracted a few different levels of event sourcing adaptation. And the first level is so-called transactional event sourcing, when in one big transaction, we are saving all the events to the event store and all read model updates. Very easy to start, very easy to implement, no magic, zero eventual consistency, but performance of such solution is quite limited. Of course, this huge transaction might become a problem sooner than later, and updating all read models will take some time. And still, I'm not saying that you should never ever implement event sourcing this way. This is actually a very good starting point. Especially if you are working on a proof of concept, or you're working on a project that maybe no one will use it, like in one of my cases. So yeah, if you want to read more about such implementation of event sourcing, just follow the link from the slide. They will redirect you to very nice articles about how to start with event sourcing, how to do this with relation database, with a lot of examples and edge cases, etc., etc. Also, as a company, we created a very small open source project with an example of such implementation. Yeah, it's in Scala, but even if Scala is not your first language, you should be able to grab the overall concepts and just copy-paste them to your code base. So, quick summary of the first level: easy to implement, easy to reason about, zero eventual consistency, but performance and scalability not so great. Second level. This time, the scope of this problematic transaction is much smaller. We are saving only events in transaction to the database, and append only writes is something that any database would love to handle. It's like the fastest possible write operation for most of the databases. So really, really fast. We definitely improve the command service side. There is a new piece on the diagram, a projector, so something needs to read new events and update various read models. And we can scale this part as well, because we can launch hundreds of projectors, let's say, but there is a cost. Since this level and further, we are entering the eventual consistency world, and this could materialize in two different problems. The first is that maybe not connected to the eventual consistency, but let's say if we launch hundreds of projectors, by accident, we could increase the event store load, because they will constantly query the database for the new events. This is a rare situation, but there is a second problem, a lag. So how often should I query my database for new events? Each 3 seconds, each 1 second? I can imagine many systems when an additional second of eventual consistency is simply not acceptable. So what can we do about this? But a quick summary before. Performance and scalability improved, but eventual consistency, increased event store load with a question mark, and lags. Another new piece on the diagram, which is an event bus. And yeah, probably you might think that introducing event bus here is an overkill, is an over-engineering. I will agree with you. If you have 3 projectors, then yeah, don't go with event bus. But there are many cases where this additional buffer between your event store and your projectors will give you a lot of benefits. So what are the benefits? Right now, you can launch, you need to query the database only once to get new events, copy-paste them to the event bus. And launching hundreds of projectors is not a problem anymore, because event buses, message buses were designed to handle such use cases, so it's okay. unfortunately, the problem of lag still remains. So how often should I query my database? Maybe each millisecond. I suppose that launching 1,000 requests per second is not the best idea. So the first solution, very naive, could be that we will save events to the event store and send them to the event bus in transaction. Yeah, transaction on two heterogeneous systems is a really, really bad idea. So quick patch for that. Right now, we are saving events in transaction and then sending them in YOLO style to the event bus. And this is the fastest possible way to fill event bus with new events. But of course, you need to provide some guarantees here, at least once delivery, so no events can be lost. And also, events order must be exactly the same. How can you achieve this? For example, by tracking event sequence number. So each event should have its own monotonically increased sequence number. If the sequence number is +1, then yeah, I can send it to the event bus. If it's +0 or -1, it's a duplicate, I can skip it. If it's +2 or more, it means that I have a gap in my events and I need to fill this gap directly from the database. In 99% of cases, you won't see any gaps, but you need to be ready for some restarts, crashes, etc., etc. And frankly speaking, implementing this is not a piece of cake. It's quite challenging, but it's possible. Definitely it's possible. So let's validate our architecture. Query services are stateless services. To scale this part, you just need to launch another instance, put some load balancer on top of it, and you're fine. Read models, yeah, you can have a separate database per read model. You can have a separate database per query, not a problem. Projectors, yeah, you can definitely scale this part because you will use some scalable event bus like, I don't know, Kafka, PubSub, whatever. Scaling event store. This part is tricky because first we need to talk about scaling command service. Can we scale this part? Command service must be consistent. And to achieve consistency, you have at least two options. First one is optimistic locking. And then you are forced to use a database that supports such locking mechanism. In most cases, a relational database, but not only. So your scaling capabilities here are basically limited by scaling capabilities of your event store. If you need to handle huge load with really a lot of requests per second, I would recommend to handle concurrency on your application level and implement something called a single writer. In this case, if you implement a single writer, you can use any event store you want. It could be a distributed database, it could be single host database, it doesn't matter. But to scale single writer principle, you need a sharded cluster solution with all its advantages and disadvantages, and I hope we will cover this as well. And this is a final version of our turbo scaling event sourcing architecture. Please do not start with something like this. Most likely, you don't need it. The goal is to show you the, the ultimate goal, the Holy Grail, and your job is to pick the level that suits your needs, and yeah, that's your job. Okay, so we know what we want to implement. Now the question is how. Quick summary: performance and scalability, very high level. Eventual consistency, yeah. Complex implementation, I will not lie, it will be hard. And if you want to read more about this locking versus single writer principle, just follow the link from the slide. It's one of my favorite articles about event sourcing related stuff. And to cover this topic fully, I should mention about two other alternatives, which is a CDC. So instead of event bus, yeah, you can use CDC. This is a very nice option, especially if you are using a single host database. But if you are using a distributed database, then I wouldn't recommend CDC because it will be a nightmare to do this in a consistent way. And because we desire so much streaming capabilities from our event store, maybe we could use event bus as an event store. And this is a link to the my CTO article about how to implement event sourcing based on Kafka. And I hope that I'm not signing my resignation letter, but be careful with that. I mean, the article is really great, and it will work super awesome for very specific use cases. but definitely not as a general purpose solution. So make sure that you understand all Kafka concepts correctly before you use it. Not covered today, but really worth to check. Command sourcing and even collaboration, let's say it's your homework. So yeah, we know what we want to implement. Now the question is how. And we have options like custom implementation, library, or framework. And if you look at event sourcing from a domain perspective, this is quite a trivial pattern. We have three main building blocks, so commands, event, state. And we just need to implement two methods. Process the command, return the list of events that will be persisted, and then apply persisted event and return new version of the state. That's why many people recommend to implement event sourcing from the scratch by yourself. I could agree with that, but there is one more problem. Your application will be production ready when you also deliver few more set but require features like snapshotting, failover, recover, debugging, sharding, serialization, schema evolution, concurrent access, etc., etc. And trust me, implementing this by yourself is a recipe for failure. I mean, I would love to create my own event sourcing framework, don't get me wrong. But at the same time, I know I will make all the possible mistakes. So just use something that's created by many programmers, tested by thousands of programmers, and yeah, do not reinvent the wheel. Unfortunately, using any framework has its hidden cost. This is an example of a JPA implementation. JPA is an ORM framework from Java world, very popular one. And the classic implementation could look like the snippet on the slide. So we have a business entity mixed with some JPA annotations. And it looks okay, right? No. What's wrong with this code? We just mixed two really important responsibilities. First is our domain code with some business code methods. And the second one is some instructions how to persist this entity. And as Uncle Bob said many times, persistent should be only a plugin to our domain. And the problem is, okay, someone could argue, so what? If I remove all these annotations, the code will be exactly the same. That's true. But this is a very simple example. And all tutorials to any frameworks are based on the simple examples. Let's say that I would like to use a map of map in my domain model. So translating such field to a JPA or to any ORM framework will be problematic. So in most cases, I will replace the map of map with something framework compatible. And personally, I hate such compromises where my persistence layer is dictating me how should I implement my domain code. And unfortunately, the same story applies to event sourcing frameworks. So here's an example of Axon framework, very popular one in Java world. So user aggregate mixed with some Axon framework annotations. The same story applies to Lagon frameworks from Scala world. User entity extends persistent entity, and check out the imports, some JSON formats. On my domain level, I don't care about JSON. I don't care about serialization. I just want to write business code. That's it. So how to deal with it? Back to the beginnings, and let's start with proper packaging. So in my domain package, let's put some all the event sourcing domain related pieces like state, commands, and events. An application package is the place for a framework or a library. If you want to read more about this, just follow the link from the style. The code base is pretty old, but the overall idea is still valid. So this way, your event sourcing user could look like the snippet on the slide. So simple case class, simple record with just two methods. And of course, this code is simplified, but the imports will be like this one. So no imports to any frameworks, event sourcing frameworks. So once again, application package for all the set stuff, and domain package for domain logic, domain validation, and in perfect world, zero event sourcing imports, framework imports. Library versus framework. Because what's the difference? Because I'm using these notions very often. So usually removing a library from your code base is much easier than removing and replacing the framework. A good example could be Akka Persistence versus Lagom. Lagom is a full-blown event sourcing framework. You just need to put commands here, events there, and Lagom will do the magic for you. unless you have a very specific business use case. And then you need to adjust this use case to the framework. Akka Persistence is one level of abstraction lower. It will provide you all the necessary technical requirements to build good event sourcing solution, but you will need to handle more stuff by yourself. At the same time, you will get more freedom. And yeah, which choice is better? I suppose I could do another 50 minutes presentation only about this topic, but the idea behind this slide is that be careful with your choice and create some proof of concepts. Make sure that you validate the existing solutions correctly. Do not follow the hype. And actually, maybe there is a choice in between. In my case, I could honestly recommend Akka Persistence Typed, which is still not a framework, but this time everything is really well organized. It's much harder to do something stupid. Okay, so we know what we want to implement, how. Now the question is where to store events. And you have options like file, relational database, event store, Mongo, Kafka, Cassandra, and many, many others. And this time the storage selection depends on the previous choice. So if I go with custom implementation, then yeah, I could use any database I want. If I go with, let's say, Akka Stack, then my choice is limited to relational database or Cassandra, which is of course not true. Many databases are supported, but for sake of this presentation, let's say that you have a choice between single host database and distributed database. And single host database, relational database seems like a safe options for the start, because everyone know how to use it, everyone know how to even maintain on production. So it's a safe choice, right? It depends. It depends on your load. If you need to handle millions of requests per a period of time, then vertically scaling a single host database will hit you. That's why I would recommend to use, or at least to analyze, distributed databases like Cassandra. Why? Because with Cassandra, you will get partitioning by design. So your data will be spread across all nodes in the cluster. You will get replication by design. In case of some node failure, you will be always able to read your events from a different node. Leaderless architecture, no single point of failure. So in comparison to Mongo, where you have a classic leader-follower architecture, and in case of leader failure, strange things could happen. And here, any node can handle any query. Cassandra is optimized for writes, so just 2 nodes can handle 100,000 transactions per second. This is, of course, marketing materials, but if it's not enough for you, then just put more nodes to the cluster, and because you can horizontally scale Cassandra really easily. Be aware that there is a growing alternative to Cassandra, which is ScyllaDB. Basically, Scylla is Cassandra without JVM. The same concepts, the same internal behavior, but this time is C++ and sister lib. And you can handle even more load. Some time ago, it was not fully supported by Akka Persistence. Not sure what is the status right now. If you follow the link, you will be able to check it. Okay, so we know where we want to save our events. Now, how to save them. And options are like plain text serialization, JSON, XML, YAML, and binary formats. And I know that you will choose JSON anyway. But let me show you some alternatives. First, let's compare plain text serialization and binary serialization. So yeah, plain text serialization is definitely human readable. It's very convenient to just select some events from the database and analyze them directly from the query. In case of binary formats, yeah, you need to create a tool that will translate it for something human readable. And of course, such tool should be created upfront. But there is nothing like a good motivation, and burning production is the best motivator you can imagine. Yeah, with JSON, be careful with some number precision issues, and other links from the slide. Storage consumption. So definitely binary formats are more compressed. The actual saving depends on your event's schema, but in my case, it was from 60 to 70% of savings on the disk space. And you could argue, okay, storage is cheap, so this is not so relevant. Yes, that's true. Storage prices usually go down, but at the same time, the amount of data we are gathering is growing even faster. And if you check the prices of good, large SSD drives for DB purposes, well, the prices are not so cheap in my opinion. Okay, most of the benchmarks are pretty consistent. Binary serialization is much faster than plain text serialization, and this shouldn't be a surprise because in case of plain text serialization, a lot of additional steps is necessary. And the last point, really important one, full schema evolution support. So with good schema evolution support, you are able to versioning your events without typical versioning pain. So no more v_1, v_2, forget about it. So in case of binary formats, full schema evolution support is on a completely different level than in case of JSON, let's say. So as you can see, binary serialization is a pretty nice option. Now, which one should we choose? Java serialization, yeah, it's slow, it's dangerous, it's boring for you out. Cryo, very nice, very fast, but it will work only JVM applications. So let's not limit our ecosystem to JVM applications. Thrift from Facebook, very nice, very rich when it comes to functionalities, but it's more or less the same as protocol buffers, and I know the second better, so let's say that we have a choice between Avro from Hadoop and Google protocol buffers. And now I could spend another 40 minutes or so just explaining the difference, but we will do this very quickly. So both of them will support many languages, but be careful because the level of support might be different. So in case of, let's say, Python, you can use only Avro with the generic schema approach. In case of protocol buffers, the support in Scala is way better than in Java, which is for me crazy. Speed, both are really fast when it comes to serialization and deserialization. Both will produce really small payload size. Both will provide you full compatibility support, full backward compatibility because you need to read old events from your event store. But you need to also have forward compatibility in case of rolling updates. And in case if you would like to introduce new events without the necessity to update all projectors at the same time. So with forward compatibility, you can update your projectors anytime you want later, which is super cool. So in both cases, yeah, you can add a field, remove a field, even rename a field. From my perspective, it's slightly easier in protocol buffers, but it's a tie again. So what's the difference? And the difference is in schema management. So in case of Avro, most likely, maybe not most likely, but it's possible to generate Avro schema based on your code base. So the code is first. And it's very convenient. You will create definitely less boilerplate code, but at the same time, Avro can pollute your domain code with some Avro specific add-ons. And also read and writer schema distribution is painful, but let's not discuss it right now. In case of protocol buffers, schema is first. And based on that schema, you will generate some code. This generated code is so ugly that you will create a separate model for your serialization and separate model for your domain, which is very nice for me because you will have clean and pure domain. But the cost of it is that you will need to create a lot of methods from something serializable to domain, from domain to something serializable. From my perspective, yeah, I can pay the price. If you want to read more about this comparison and about all the slides I just skipped, just follow the link from the slide. Okay, last big question is what we should put to the event payload. And most people will start with delta change. So delta event, let's say that we would like to emit user funds withdrawn. And in that event, we will put only the withdrawal amount. This is okay, it will work, but from my observations and from, let's say, projector's perspective, it's quite painful to process such events. Let's say that I would like to send an email to the users if I spot that the current balance is below some threshold. So it will be nice to enrich such event, user funds withdrawn, with a current balance. This way, The projector implementation is really simple. I don't have to calculate anything. I don't have to query external resources. It's really, really easy to create new functionalities. So from my perspective, events enrichment should be a default choice. The extreme version of events enrichment is to put the whole state to the event. I've done this once. Yeah, I'm not sure if that was a good idea. In this specific case, it sounds like a pretty reasonable. But the cost of it is that, yeah, huge payload size and pretty complex schema to support in future. And besides business information, most likely you will put some technical metadata to your events, like a sequence number, creation timestamp, event ID for the duplication, command ID that was the source of this event, and correlation ID if you want to track the whole business process. So yeah, that's the technical metadata. So now we know everything, what we want to implement, how, where to store events, how to store them, how to compose the event payload. So let's introduce some event sourcing in our ecosystem. Where? Everywhere. No. This is the first major problem with event sourcing adaptation. As you already noticed, this pattern is quite powerful, but at the same time quite costly. So in your core domain, you should choose even some subset of this domain, most likely the part which brings money, and maybe this is the candidate for event sourcing, maybe not. So remember about this slide, and now we could focus on more classic problems. And the first one is the time required to replay the state. And many people ask about this. Surprisingly, this is pretty fast operation. Whoa. 1 second. Yeah. So surprisingly, this is a very fast operation to load, let's say, 100 events, even 1,000 events, and replay the state. But if this is a problem for you, make sure that your event sourcing framework supports snapshotting. Snapshotting is basically saving the snapshot of the state every X events. And this could be a separate abstraction, or let's say it could be in the form of the event. This is just a detail. Another solution could be to keep everything in memory. So once you load the state, it will wait to handle next command, next command, next command. And that's why event sourcing based on actor model and Akka stack, it's so fast because everything is in memory. So it's hard to do something faster than that if you don't have to access the database every time you need to replay the state. For more information, this technique is called write to cache, and of course an article about it for you to read later. Okay, because you keep everything in memory, you should accept or could accept out-of-memory exceptions, and out-of-memory exceptions are pretty boring in Java. Not sure how it's in your ecosystem. So make sure that you are not doing anything stupid with your state and learn how to use some memory analyzer tool, and you should be fine. The next question is, should my state be immutable or not? By default, of course, immutable. It's much harder to do out-of-memory exception this way. But as always, it depends. So in my case, when we were using immutable lists, we were able to deliver 17 operations per second. And then we switched to good old-fashioned Java 3 map, 2,200 operations per second. And this difference is so huge that it cannot be simply ignored. That's why we go with mutable state. Still, an actor is the guard of the state, so I'm pretty comfortable with that choice. Fixing the state. So from time to time, you might face the problem that your state is broken, and how to fix it in event sourcing. And there is a temptation to update events in database. No, events are immutable. They shouldn't be changed. So in this case, you should apply something called healing command. Could be a semi-technical, semi-business thing, could be a business thing. And this way, this command will most likely produce healing events, and that's the recipe for fixing the state. This one is boring, handling duplicates. Oh my God, this is a nightmare in a distributed systems. Let me tell you a story. This is a fairyland. And this first unicorn is exactly once delivery. And the second one is transaction between two aggregates. None of them exist. And, you know, I'm a happy father of twin sisters and a boy. But let's focus on the twins. So when I'm saying that there's no such thing as exactly once delivery, trust me, I know what I'm talking about. So if someone is telling you that you can achieve exactly once delivery in a distributed systems, yeah, either this person is lying to you or not telling the whole truth, or this will be extremely slow and a dangerous thing. So why duplicates? First of all, we can create duplicates here because we have at least once delivery. But even if you are able to filter out duplicates in this part, our projectors, consumers should be ready to handle duplicates anyway because of some restarts, some repartitioning, some crashes, etc., etc. So always be ready for duplicates. And the easiest way to handle them is to have idempotent updates. So in this case, processing the same event twice will not change anything. This is super cool, but some projections are not idempotent by definition. So let's say that we are calculating an average. So in this case, processing the same event twice will corrupt the result. And the solution for that is to, once again, track, basically to achieve something called effectively once delivery or deduplication. And you can do this by tracking a sequence number. So if the sequence number is +1, then I can process it. If it's +0 or -1, this is a duplicate, I need to skip it. If it's +2 or more, in this case, the only thing projector can do is to throw a very nasty exception because we have a gap in our event bus and the problem is on the producer side. Be aware that you need to store the current sequence number with the read model update in one transaction. And surprisingly, not all read model databases support such transaction. For example, Redis is a very good example here. Transactions in Redis are something completely different than in relational database. So be careful with that. If you don't have sequence number, then you can use event ID for the duplication, but then you will need to store some history of event IDs. Okay, broken read model. So when you can break your read model, two main reasons for that. Software reasons, so a bug in the code or not handling duplicates, and hardware reasons. So some read models are more fragile than the other ones. And Redis is a very good example once again. In case of Redis, you should expect some data lost, always. And actually quite a lot of them, depending on your configuration. So thanks to event sourcing, you can always drop the whole read model and recreate it from the beginning. This is super feature, super important feature of event sourcing. I think the most important one. It saved my very many times. Unfortunately, sometimes processing billions of events, especially in case of hardware issue, will take a lot of time, and we don't have this time. So in this case, if this is a hardware issue, we could use a technique called manual offset management. So we are saving in the same transaction the read model update and current offset from the message bus. Yeah, it's technology dependent. It's possible in Kafka and few other message buses, but not all of them. So in case of some hardware failures, we just need to read the latest successfully saved offset and start processing from that offset. Multi-aggregate transactional update, the second unicorn. So if you need to handle a use case that you need to update two aggregates at the same time, it's time for a pause. Start with rethinking your aggregates boundaries. Maybe your aggregates are too thin, and if you combine them together, you will eliminate this problem very easily. Sometimes your aggregate boundaries are fine, and you still need to handle this. And forget about transaction. The only way to do this right is compensating action. And compensating action can be optimistic or pessimistic. Though these are not official names, I just made it up to explain you how you can approach to this problem. So let's say that we are building very simple application for selling tickets to some cinema shows, and we have two aggregates. A user account, which represents user with some funds that we can charge, and cinema show where we need to select a seat, and we cannot sell more seats than available. So in case of pessimistic compensation action, from the user perspective, first we will charge the user, then we will book the seat, and it was the last seat, so seats are sold out. Unfortunately, our applications are used by many users concurrently, so right after charging the first user, another user can book that last seat. So it will be nice to have a transaction here. No. Just look at it as two separate microservices. We know that transaction between two microservices is painful, so the same story applies here. And we just need to apply compensating actions, so refund the money. In case of optimistic compensation, first we will book the seat, and then we will charge the user. And in case of concurrent booking, we will enter the overbooked state. So now the question is, should we charge the user? I suppose in case of cinema business, well, it's not a good idea. But in case of flights and plane tickets, it's part of the business strategy. Overbooking is fine. So different business needs different solutions. The one thing is missing here, how to implement this, and for that, most likely you will use Saga pattern. Saga could be implemented as a choreography, which is basically consuming 2 or more stream of events and checking for some inconsistencies, or as a orchestration where you have one single place with the whole business process. The first one is definitely easier to implement and easier to start. The second one is nice in the sense that you have one place with the whole business process. Unfortunately, implementing Saga, I mean, the pattern is really easy to understand, but implementing it is really challenging because Saga must be persistible. It must survive restarts. Events orders, you cannot assume any events order. There will be always some time window limitation. So let's say that I'm checking for inconsistencies within 10 minutes window. And after that, I'm applying compensating action. But some events might arrive to us after 12 minutes. That's why compensating action must be commutative. So few more links about Saga pattern for you. It's a really huge topic. Okay, event sourcing and Rodo GDPR. Yeah, your application should give user something called the right to forget, and how to do this in event sourcing where you cannot delete events. To be honest, you can, but you should avoid it. So the technique here is called data shredding, where you can encode some sensitive information, and if you need to delete user data, you just need to delete the encoding key. Sounds easy, but not so easy again to implement because managing those keys is a pain. Not to mention about some retention policies of your message brokers, backups, logs, and data before Rodo. A piece of advice from my side, do not use event sourcing for sensitive information. Most likely crude application is fine for it. And the only user data should be a user ID. Okay. In our final version of our architecture, we are using sharded cluster, and with any cluster, you should expect a nasty problem, which is a split brain. Who knows what is a split brain? Okay, few people. So let me explain it very shortly. Let's say that we have a cluster with 5 nodes, some load balancer on top of it, and load balancer is a dummy machine. It will just route all the requests to all nodes in the cluster in, let's say, round robin fashion. So request to update user with ID 1 will be redirected to node 5 from the load balancer, but node 5 is in the sharded cluster. So this node is aware that actually node 1 is responsible for user 1, so it will redirect this command to node 1. And then we have a disaster in our DC, a broken switch or something like that. From the load balancer perspective, everything is fine. So all nodes are working okay, all nodes are green, but node 1 and node 2 cannot communicate with 3, 4, and 5. So they will create 2 separate clusters. In this case, command to update user 1 from node 5 will be redirected to node 4, because in this small cluster, node 4 is responsible for user 1. But next command could go to node 1, which is still responsible for user 1, and there you have classic split brain. And fixing the state after such failure is really, really painful. So cluster best practices, always remember about the split brain. In case of Akka, there is a dedicated solution for that, which is split brain resolver, and you need to enable it and configure it correctly. Also create very good monitoring and alerting of your cluster. You should know 24/7 what is going on. Perform a lot of failover tests on dev tests and even on production. Create your own chaos monkey. And cluster should be deployed not only on production, but also on dev and staging environment, just to test it more. And keep it as small as possible when it comes to code base and number of nodes. If you can move something to a stateless service, just move it to a stateless service. Summary of this whole presentation. Event sourcing is great. It's awesome. You will love it the second time you use it. The first time it will be painful. That's why carefully choose your event sourcing library or framework. Really, take your time, create proof of concepts. There is no perfect database for event sourcing, only a good compromise. Understand events command state is schema evolution. And really, once again, take your time. I'm not talking about hours here. I'm talking about days. This is really important topic. I know it's extremely boring, but spend some time on it. Eventual consistency is your friend. Do not fight with it, just learn how to deal with it. Scaling is complex. Yeah, launching Kafka cluster, Cassandra cluster, Akka cluster, etc., etc. It will require a lot of work. But once you do this, the reward will be proportional to the effort. This whole event sourcing is basically turning your database inside out. So once again, this asynchronous event-driven communication with event sourcing is really nice. Unfortunately, we didn't cover this topic. And the last point, a little bit philosophical. If you implement your first system or second, where the core is basically processing a stream of events, you will realize that all big players are using exactly the same techniques. So Twitter, Facebook, Netflix, whatever. Most of the DB engines are using exactly the same techniques. Why? Because this is the recipe for building reactive, easy to scale, distributed systems. And definitely worth to expand your toolbox with event sourcing. It will change your mindset in a good way. And that was the last idea I want to share with you. If you have any questions, I'm here for you as well on Slack. Thank you. Questions? No questions.